introduce the fundamental concept of the steady state error. So basically, last time we exercised is the ES as by definition is T approaching to infinity of ET. And this one, by applying Laplace transform theory, we can have this, and this one being used in our exercise. Okay. So today I'm going to go over by using this fundamental concept in detail to simple systems. And for doing that, I want to define new terms. This one is called the system type. Or type of the systems. Basically, the system type, we say the system is type 1, type 0, type 2, type etc. Basically, it's this. If we consider a system, this system can be any system, can be an open system, and can be the closed loop system. Okay, so using the GS, and if in certain way it can be expressed by this a polynomial. Let me make up one. Okay, so say this is a k times say T1s plus 1 and T2s plus 1, etc. Okay, and the denominator here is a particular, say, let me say this is whatever, let me make up one. Okay, Tns plus 1 and multiplied and with something. In particular here, I want to have is this. In the denominator, it also have multiplication of a singular s and to whatever the degree here n. And so that means the system GS is of type n. So that is the definition of the system. Okay, so simply you look into the denominator whether they have a multiplication of a single s and to n degree. If there's nothing, then basically n equal to 0. Okay, so example is this. So if GS equal to s plus 1 as s plus 2, then basically that is the type 1 system. And for example, GS equal to say s plus 1, s3, s plus 2. So basically this is the type 3 system. Okay. So that is the definitions of the system type. So that is the definition 1. And another equivalent definitions, and this definition is a little bit obscure. So we can use the example to demonstrate this definition. So in this way, I want to keep the definition for a while. So let me write it down here. Okay, and later I'm going to erase the portion there. So this one is a system type n. It's the lowest degree n of the input Tn resulting in a non-zero steady state error. Okay, if we try to understand this definition literally, it's hard. It's kind of hard. So I keep that definition for at least for half hour, and then we can begin to look at for some calculations and to do this one. And before we're doing that, and I can tell you the two definitions are identical. So really depends on how you look at that one. The first definition is looking at the system type from the S domain. Okay, the second definition is look at the system from the time domain. So let me get into the more calculations here. So here in our exercise, let me use a very particular system. This is this. So here I would say let's look into a special system, and that is, for example, so this particular system is this. So GS and so here the output is YS and input is RS. Everything is in the S domain. So here this is our ES here. Okay. So here in earlier we know we can calculate the steady state error is limit as approaching to 0 and S times ES. Okay, we'll stick with this one. And what is ES? ES, by reading through this information, is simply for this particular system is R minus Y. Okay, and what is R minus Y? And so here we have to do it. So from here we can do this kind of scratch calculations. Y equal to G times E equal to R minus Y. So here we can do this, try to find the transfer functions GR and Y, 1 plus G. So here Y over R equal to 1 plus G and G. Okay. So here we can do these simplifications is R minus Y minus Y over R. Okay. So we plug in the information here, R times 1 plus G times 1, right? So therefore this one is simply is RS. Let me write it up. Okay, so therefore for this case, the ESS simply we put into this formula S times R of S and 1 plus GS. Okay, again, this calculation is particular for this particular system, for example here. And if you know the procedure, you can apply the same steps to other general systems. Okay, so here I want to emphasize the G as is the open loop. So that means that is the system without control. We call the open loop system. Okay, the open loop system is a system without control. Basically, the open loop system is the original system we want to control it. Okay, so sometimes we call it original. We'll just simply call it an open loop system. Okay. And so here you can see basically in these calculations, everything will depend on the first one. What is the type? What is the input here, and also will depend on the G. And pretty much we can try to include the definition of the G here and see what happens. Okay, so here the follow-up, I'm going to base upon the two varying parameters to see and to do a little bit more scenario study. So based upon that case, and let me say the ESS, let me write it up here again. So now for this case, I want to study is say for the unit step input. The follow-up in the following 10 or 15 minutes, I'm going to talk about the different scenarios. The first one is the unit step input. For the unit step input, and that means the RS equal to 1 over S. Okay, so with this number, we see what happens. So under these situations, ESS equal to limit S approaching to 0, S times, and here I introduce RS equal to that, and 1 over GS. Right? Okay, so that's the calculations.
Professor?
Yes.
There was 1 plus GS and now...
Oh, sorry. My mistake. Good. Okay. So in this way, right now we can apply the algebra on this limit. So here we cancel the S here. So from here, basically this one is equal to limit S equal to 0 apply onto the whole terms, and here the constant term won't be affected. So let me put into the limit into here. Okay, be good. So we simply do that one, and by this way, I'm going to introduce the term. This term is used in our textbook in many places throughout the chapters. So you better to adopt this one. So this term, we defined it as called the KP. And KP is called the static positions error constant. And that's a very long name, and I never be able to memorize this one. So I can tell you every time I see that one, I go to the index and figure out what is that for. But that is not important. But important thing is the follow-up calculations. Well, the definition is important because sometimes if I will assign the homework, and sometimes it will appear this kind of things, and you should know where to look up what I mean or what people mean. Okay. So try to pick up those definitions. So basically, with this definition of this constant, it's basically here the ESS can be written by 1 plus KP, right? Okay, with this one ready, then we can see. So now KP will depends on the GS. So let me tabulate the result here, KP, and then this is ESS. Okay. So for GS, if this is the type 0 system. So what is a type 0 system? Type 0 system basically is something like here, something like the S plus 1, S plus 2, and S plus 3. But here, this multiplication of S is 0. That's called the type 0 system. Okay. So once on this one, you can see basically for the type 0 system, once we have the S approaching to infinity, basically, the type 0 system for KP, the value is how much? It's certain finite value. Sometimes could be 0. Okay. Okay. Sometimes could be 0. Sometimes could be constant. Depends on the terms. So I would say the ESS basically simply is 1 plus KP. Depends on the conditions. Okay, so the KP, the value could be 0 or other constant. Okay, and for type 1 system, the type 1 system basically is something like this. And so for that case, eventually, because there's an infinity in the denominator, so KP definitely will be 0. Sorry, my mistake. I confused with that one. Can I start over again? Basically, this value, this one, let me modify this one. Okay, so let me start over again. For the type 0, basically is this. Okay, and Kp by definition is s approaching to 0. So for type 0 system, you can see the Kp will be always a certain constant. And that constant is non-zero constant. Right? Okay, so that is Kp1. For type 1 system, is like this. So for type 1 system, Kp by definition is like this. So we have something divided by 0 in the denominator because when s approaching to 0. So basically it's something divided by 0, so that is go to infinity as a Kp. And under this case, this one is 1 divided by 1 plus infinity, 1 divided by infinity, this is 0. Good? Okay, at this moment we can stop a little bit and we think about what is the unit step input. The unit step input basically is RT equal to T to the 0, right? What is the unit step input? Unit step input is this T, this is the RT, and that's a constant 1 here. Constant 1, basically this one equal to 1, right? Okay, so for type 0 system, we look up these definitions. A system of type n, so you can see this is a system of, right now we're looking into what is the system. This is a system of type 0, then that is non-zero constant. So for this case, when system type equal to 1, it becomes 0. So we put into this definition, the system type n is the lowest degree of the Tn such that resulting in non-zero steady state. So basically that definition fit into this case, right? So therefore, for this case, GS is type 0 system. Okay? So GS is a type 0 system, and from this one we can see. Okay, so now we keep doing this one. This is a type 2. For type 2, basically this is s to the square. Again, that is something divided by 0 square, and definitely that is much larger infinity here. So again, this is 0. Okay, so now we can have so for type 0 systems, and if the system is type 0, then it will be able to, how to say that one? So this is the input kind of the input. This input is constant level, and basically the input is keeping constant. Which means the magnitude of the input won't be changed. It's constant over time. So in this way, we would say this dynamic of the input is slow. Basically, it's not changing. Okay, so here I'm going to say something slow. That means the change in dynamics is slow, and fast is the change in dynamics is very fast. For this case, basic changing in dynamics is nothing, 0. And basic 0 is very, very slow. Okay. For type 0 system, it's going to follow up a slow input and have the steady state error. What I mean? So for type 0 system to follow up a very slow command and still fall behind or still persist, not closely follow up, something like this. A type 0 system try to follow up an elephant. Try to keep pace with an elephant, but that system cannot, still fall behind 1 step or ahead of the 1 step, but cannot exactly keep the pace with. That is what the type 0 system is. So from here, can you say the type 0 system is very sluggish, is very slow? Can you get a feeling? Because for type 0 system, to follow up this command, it still have a steady state error, right? What kind of this command? This command, as I mentioned already, that's a slow system. So a type 0 system try to follow up as this kind of the slowed input and still exhibit certain error in following. So which means just you can imagine this is certain slow dynamic, could be certain elephant, and certain animal to follow an elephant cannot keep pace with, so that animal should be even slower, right? So from here you can see this type 0 system usually is a slow system. In dynamics, it's a very slow system. Okay, and so for slower system, and for type 1 system, you can see type 1 system is going to follow up this input presenting 0 steady state. So that means for type 1 system, it's going to follow up the dynamics precisely without any error, right? So that means this system is more agile. It's more agile, be able to follow up whatever the command is given here. And not to mention type 2. Type 2 is much more agile than type 1. So that is the physical meaning behind this table here. Okay, so think about this, and let me continue to the second scenario. I'm going to have the 2 blocks because I have 2 more scenarios. The second scenario is for the ramp input. For the ramp input, basically is T and RT, and this. So this is slope 1. So basically the RT equal to T. Okay, so right now I'm writing up is this. So basically, right now we'll check against this definition. Right now we're looking for n equal to 1. We see what happens. Okay. So that means the RS for this case is 1 over S squared. Okay. So we see. So ESS will be equal to limit of S times, and again follow up that one. 1S squared and 1 plus GS. Okay. So right now we do these simple simplifications. So basically we can cancel S here. So leaving 1, and then we multiply this S into the denominator here plus GS, right? Okay, so sorry, here is a limit that's approaching to 0. So again, from here, we do the calculation. We have this limit applied to the individual terms there. So basically that becomes limit as approaching to 0, S times GS, right? Because this term becomes 0. Good? Okay, so this term, again, we have another definitions. This one we define as called the KV, and KV is called the static velocity error constant. And why we call it velocity? Because if you remember in Laplace transform, when we s multiply with x over s, equivalent is x dot t, right? So that means this multiplied s with s, that basically is derivative in the time domain. So that's the reason why we call it velocity. And that's the reason for this. Okay. So again, for this case, we still have do the same exercise, GS and KV and ESS here. Okay. So for GS, if that is a type 0, for GS is a type 0. What is a type 0? So basically here we can say GS, say for example S plus 1 and S plus 2. And for type 0, that is 0 here. Okay, so that's the GS. And then KV basically equal to S multiplied with this one and limit as approaching to 0. This is our KV, right? So I make up one example, say this is our type GS and that is type 0. I make one example here. Okay, so we see what happened. So from here you can see this one is constant and making s, so basically for this case is 0, right? So kV is 0. kV is 0, then for this case the ESS basically is simply is 1 divided by kV, which is infinity. Again, what this means? Type 0 system has been so sluggish, so slow, and by tracing a constant input, it has appeared the constant steady state error. So even for the faster input, changing the input, that won't be able to follow up. So that will gradually fall behind and fall behind eventually, eventually the steady state error will become infinity. Got it? Okay. So type 1. If this is type 1 system, then we can do the exercise here. So type 1 system basically appears as a 1 here. Then we do the calculations. I can wake you up. I can wait for you for a little second. For type 1, you can write down here. Okay. So I'm going to cancel this, basically this term, cancel this term out, right? So this one leaving this term as a constant. So basically this is a non-zero constant. So kV is non-zero constant. Basically here this is 1 over kV, and that is not equal to 0. Okay, type 1 system is a little bit faster system. To follow up this one, basically it's able to follow up, although fall behind or ahead a little bit, although it cannot precisely follow up it, but it's good enough. Got it? Okay, then we see type 2. Type 2 system is something here is 2, right? So now we simplify the S and with this one, so basically we cancel out, so this one, we cancel out this one. Okay, so we have S divided by 0 here, so basically this becomes infinity here, kV. So kV infinity basically is 0. So for type 2 system is fast enough. It will be able to completely, precisely follow up this command without any mistake, without any error. So the system will be able to exactly follow up whatever you go, I just follow you. So this is a very fast system. Okay. So now we can continue to 3, and that is the unit parabolic. So that is T, and RT will be something like this. So that is T squared. Okay. So RT equal to 2 T squared over 2. Sorry, let me change. Oops, sorry. T squared. 2T squared. Okay, so that means RS will be equal to this one. So not unit, only parabolic. Okay, so the same thing, ESS will be equal to limit s approaching to 0, s times RS and 1 plus GS here. So here again we plug in what is RS. So S times and 1 S3, 1 plus GS. So here again we multiply into, so we cancel this one, this become S squared, and then we multiply that S squared into denominator, S squared plus S squared GS, and 1 here, right? Okay, and this thing becomes 0. So basically this is limit S approaching to 0, and 1 times S squared times GS. And again, from here you can guess, we have another definitions. This one is defined as the Ka, let's call it static accelerations. Error. Constant. Again, why we call the accelerations? Again, if you remember in Laplace transform, x dot times x over s, and that is x double dot converting to is this one and minus s times x dot 0, and minus s minus x 0, right? Something like this one. So basically, we're picking up this form, so we know in the s domain multiplied with s squared, equivalently, that is the double derivative. So here we call this accelerations here. So the same thing, we can play around the GS and KA and ESS here. So again, we're starting from type 0. So type 0, before we do the calculation, from here you can see this one should be infinity because this input is even changing in dynamics even faster than this one. So type 0 cannot follow up that one, not to mention this even faster input. Right? We can do the calculation and see. So for Ka, so again, let me do that calculation here. How about this? So let me assume GS equal to S plus 1 and S plus 2. Okay? So this is GS, and for type 0 system is S0 here. And so that's a GS, and let me kind of box this one. So multiply square here, and limit. Okay, so this is Ka. Okay, so this is Ka. So for type 0 system, you can see for type 0 system, this becomes 0, Ka becomes 0, right? Okay, so Ka becomes 0, then we plug into here, ESS is infinity. And for type 1 system, this is become S1 here, type 1 system. And then we multiply with this one again. From here you can see Ka again equal to 0. Okay, so K is 0, this is infinity. And for type 2 system, this is 2 here. And so from here we cancel this term, S squared cancel with this one. Basically Ka become a non-zero constant. So basically this one is 1 over Ka, and which is not equal to 0. So type 2 system, up to here, type 2 is a faster system, and for this case, it will be able to follow up the parabolically changed dynamics input. Okay, so for example, here you can use the pilot of the flight jet. For example, if he plays certain very kind of the positions, something, if they change very fast, and if you can follow up that one, then basically that system is very agile. Okay, so that's an example that we can continue to play with. So say if this is type 3, we see what happens. If for type 3, that is S squared, and this is 3 here. Okay, so type 3 is a very fast system. I would say this one will go to 0, but we can do the calculation. For Ka, we cancel this one. Basically, this is S. So for this case, Ka becomes infinity. Right? So for this case, for type 3, Ka becomes infinity. This becomes 0 naturally. Okay? So now for this case, this is the input, and to t to the 2, that is n equal to 2. Corresponding to n equal to 2, then for making the things the minimum degree of the n, making the steady state the non-zero steady state error, that is this case. So that is type 2. So from here again, we confirm these definitions, and from here this system type n basically pertaining to the order of the n that has producing non-zero steady state error. From here we can see this one. For this case, this is the n equal to 1 here. Okay, so the minimum degree to make the non-zero steady state error is this case here, and that is type 1. And in my personal opinion, and because most of the time in this semester, so we're working is the transfer functions in the S domain complex plane, which means in terms of parameter S. So I would say the definition 1 is easier for people to pick it up. Okay, and for the second definition, unless you're working in the time domain, and then that will be convenient. Okay, so that is for these sections.